Welcome to our new in Wolfram Language 12 webinar series. Today is the second session in a four-part series that covers significant areas of new and expanded functionality in Mathematica and the Wolfram language. My name is Jamie Peterson, and I'm the Technical Programs Manager for Wolfram U, a free and open learning hub that features interactive courses, video classes, and webinars like this one. Thank you for joining us today. Today's topics are all about the extended capabilities of the Wolfram Knowledgebase, the world's largest and broadest repository of computable knowledge, which powers Wolfram Alpha and the Wolfram language. Joining us are Tony Schindler, developer of the Entity Framework, Andrew Steinecker, lead developer with our Scientific Content Group, Alan Joyce, Director of Content Development, and Keiko Hirayama, developer for Biology and Medical Content. We'll be taking a deeper look at the new entity query functionality and also at food and nutrition data, cultural and historical entities, and computable knowledge in biology and medicine. Let's get started with a poll question that will help us understand who's here in the audience with us. This poll question asks about your experience with the Wolfram Knowledgebase. You might be familiar with the Knowledgebase from your use of Wolfram Alpha, or from your use of Mathematica or the Wolfram language, or maybe both. The poll should be showing up on your screen, so go ahead and check whichever answer applies to your situation. Okay, I think we're probably ready to share those results if you're curious to see who's here with us today. As you can see, lots of Wolfram Language Mathematica users, which we're very happy to see. And then also a good number of people who have used either the free version or the pro features, which are subscription-based of Wolfram Alpha. So thank you everyone for being here. We really appreciate that. We think we will have something to benefit everybody. The next poll I want to ask is about the version of the Wolfram language you're using. So for those of you using the Wolfram language, we're curious to know if you're using version 12 already or an older version. In his version 12 announcement blog, Stephen Wolfram wrote that the curated knowledge base in the Wolfram language is vast and continually growing. With every version of the Wolfram language, we're progressively tightening its integration into the core of the language. So if you're using an older version of Mathematica, you may not be aware of how conveniently this data can be accessed in version 12, and we're excited to show you some of that functionality today. And wow, looks like a good majority are already using version 12, which is terrific. You have everything at your fingertips then, ready to explore the things you've seen today. I'll share those results with you in just a second. There we go. So yeah, 61% at 12, and then a good number at 11, and then some using older versions or have not used the Wolfram language or Mathematica yet. So that's really great to know. Thank you. So I think we're ready to get started with our presentations. I'm going to pass the microphone to Tony Schindler now, and we're ready to get started. Thank you.
Hi, I'm Tony. I'm working on the entity framework as well as semantic technologies, think the graph query language Sparkle. I'm going to give a quick introduction to entity queries, new entity query functionality. So here's the outline. So for someone who might need a refresher in entities or has never heard of them, a quick introduction to entities, properties, and classes. And after that, we are going to see some query primitives. Queries means filtering of entities or sorting them, aggregating and combining. Those are primitives because you can combine those primitives to form more complicated queries. And then I'm going to mention the backends that you can use with those entity queries, as well as Sparkle, how that relates to entities. So to start, let's see an entity. Here's the natural language interface of the Wolfram language. You can bring it up, for instance, by hitting Control equal, and then you can type anything that comes to your mind, in this case, a zebra. And when you hit Enter, it gives you one of potentially many interpretations. If you don't give enough context, you might get multiple interpretations, as in this case, but I'm happy with interpretation. I wanted to have an entity that represents zebra. And then what can we do with an entity? Well, we can look up properties. For instance, the maximum speed and an image of a zebra. Yeah. New is the ability to specify computed properties using an entity function. That means you can use an arbitrary computation in any place where you could also use a property. Yeah? In this case, we are getting again the maximum speed and image and the color negated image. Yeah? And we see a zebra still looks like a zebra after that operation, except for the eyes maybe. Yeah? This looks like a simple operation, but later we'll see how useful that is. Yeah? The next concept after entities and properties are classes of entities. Here's an example class. The class of all planets. If I evaluate it, you see that nothing happened other than formatting. That's good because an entity class is just there to represent the collection of entities. Yeah? If you want to know what the members are, you apply entity list to it. Yeah? You might be wondering what order those entities are in. Yeah? They seem to have an order, but the order in entity classes, as we have known them since earlier versions than 12, don't have a specified order, so it could be in any order. Yeah? But we'll see later how we can, or what we can do about that. Yeah? We can also ask for properties of classes. And what does that actually mean? That means give me that property for all members of that class. Yeah? In this case, I want the image for all planets. In this case, we don't see yet which entity those images correspond to because the default result form is a list, but we can change it to an association. Yeah, to see that, for instance, this one is Earth. Yeah. Now, as I mentioned before, entity classes don't have an order defined, but with the new construct sorted entity class, we can order or define that the order of the entities in that class follow that of a certain property. Yeah? For instance, I can sort all planets by the distance from sun. Yeah? And now I can be sure that the entities that I got here are ordered by the distance from sun. But now comes the power of the new entity function. I can't sort only by predefined properties, but by an arbitrary computation. For instance, I can sort the planets by the ratio of the distance from sun to Mars. Yeah, so you see the entities came back in a different order. The next operation is filtering. Yeah, we start with a class or a type, which basically means all entities from that class. Yeah, and then we apply predicate to all of those entities to figure out which entities should be in that class. Yeah? In this case, we are finding polyhedra with more than 150 faces. Yeah? And again, as with the entity classes before, those things don't evaluate. And that's a feature of all of those new query functions. Yeah? So you might want to build up complicated queries from simple ones. So you don't have to worry about them evaluating before you're done writing your query. Only once you do something with those classes, yeah, is the query actually evaluated. So in this case, I'm asking for the image for all of the entities in that class. In that moment, the query is executed and the image retrieved. Yeah? So image, yeah. So those seem to be the polyhedra that have more than 150 faces. Now comes the first complicated or more complicated example. This may be the second most complicated example. Aggregation. What does it mean? Let's start simple. We are starting with planetary moons, and we want to group all of the moons by the center they are orbiting. And then for each of the groups, the groups are defined by the center, we want to count the moons, and we want to determine their total mass. And we can achieve that by saying here, the class that we start with. Optionally, a group by property or computation. Yeah? This is optional because sometimes you want to count or total everything. Yeah? In this case, we want to group by center. Yeah? And then we define, for instance, the moon count by getting an empty list of properties, the moons, and what do we get back? Yeah? A list of empty lists, but a list has the right length, so that's the count of the moons. And we can also total the mass of the moons in each group. Yeah? And now we can apply entity list to this new aggregated entity class. And you can see that this is really a new kind of entity. First of all, in the formatting, in this little symbol, yeah, which somehow seems to indicate aggregation. But also in the tooltip, you see that the first argument of entity is not a string anymore, like in previous versions, but a query that defines the type. Also, the canonical name, which is the second argument, is now an expression, namely the value of that grouping predicate. Yeah. And what are the properties? Well, you have three properties. First of all, the thing that you grouped by, because it's a constant across each group, so you have the orbit center, and then the two properties that you defined, the moon count and the total mass. Yeah. And let's take one of those new entities, let's say the group of moons orbiting Mars, yeah, and ask for a data set. We could have chosen association, but just to show you different result forms. Yeah? And the orbit center is, as expected, Mars, yeah? And it has two moons and, well, that mass. And now comes the most complicated of all of the query primitives. Yeah? It's combined entity class. But there are many ways in which you might think of combining. Well, let's say you have a list of 2 elements and another list of 3 elements. You might think that you get 5 elements by combining them. You should place one after the other, but that's not the combination that we are talking about. We are talking about combining in the sense of a relational database join. So to explain that, let's start with Pokemon, because Pokemon are a tool for explaining complicated stuff. Yeah? So we'll get for this tentacle the image just for your illustration, but also the type. Yeah? And what do you see? You can see that a Pokemon in general can be of multiple types. Yeah? And now let's look at another property, the attack. Yeah? And now you might be wondering, what is the average attack for a Pokemon of a given type? Yeah? If the type were singular, that means every Pokemon were just of a single type, the answer would be easy because you could just group by that type and then average the attack. But in this case, we have to do something more complicated because the type is a list. Yeah? So we want to form all Pokemon and type combinations, yeah? And then after that, group by type and compute the mean. Yeah? And we do this with a combined entity class, which is a join. And a join is basically an outer product, which just means form all the combinations of Pokemon and Pokemon type and filter those combinations by this predicate. Yeah? And to see this new entity, you see there's again a new type of entity. It has a different symbol, yet again another symbol. Yeah? And this seems to be indicating combination. And the type is again a new kind of type. It's not a string, but it's the query that you started with. And the canonical name that you can see as the second argument of entity is composed of the canonical names from those entities and those entities. And you can look at the properties and you can see that it has properties from both types, some from Pokemon and some from Pokemon type. Yeah? And now we can compute the mean attack by aggregating over the class that we started here. Yeah? So now we see the power of the new query functionality because we are able to nest arbitrarily those query primitives. In every place where you can use a class, you can use a query primitive, which is itself a class, so you can reuse it. Yeah? So now we're grouping by Pokemon type and computing the mean. And Here we see the result. Let's get that numeric. Those are not sorted yet, but we could sort them if you like. Yeah. But there's another way. We can define a sorted entity class, sort by attack, and get the same result. Yeah. So we have just nested a combined entity class with an aggregated entity class and then a sorted entity class. Yeah. And you can continue doing that. Now about backends. So the Wolfram knowledge base contains many built-in types, and you can apply those entity queries to any of those types. You can build your own entity store, register it, and then apply those query primitives to those entities, or even combinations of your entities and built-in entities. Or if you have a relational database, you can make an entity store out of it and register it and apply those query primitives to it. And actually, those query primitives were invented to support querying relational databases. And now a quick look at Sparkle. Sparkle is the graph query language of the semantic web. Normally, you would query RDF, that means Resource Description Framework, data using Sparkle, but we are trying to apply, and this is very experimental, Sparkle queries to entities. Yeah? And if you know Sparkle already, it consists of triple patterns. And in this case, I'm trying to look for triples that have as a subject, that means the thing that we're describing, carbon, then as a predicate image, and this is a variable. That means when we apply this query to the domain element, yeah, we get all possible bindings for the image variable. In this case, we got one image. This would have been easy if you just do it like that. Yeah? But now, if you want to do the reverse query, it would have been a little bit more difficult. Using Sparkle, it's still simple. Yeah? Doing a reverse query just means write a triple that has a variable in the subject position, then the property, and then the value. So that means we're trying to find all the physical systems having 4 degrees of freedom. And we see, for instance, the inverse distance potential in 4D, which you could use, for instance, to model 4-dimensional hydrogen atoms. And the last slide, here we're redoing the Pokemon example. Yeah? The query looks much simpler because when we apply Sparkle to entities, we automatically flatten list valued properties. Yeah? That means you don't have to worry about the joins. Yeah? And we're retrieving, using that query, the attack and the type of each Pokemon. Yeah? Then we're defining an aggregate, which looks pretty similar to the aggregated entity class. The argument structure is the same, except that in Sparkle, everything is an operator. Then you compose both queries and apply to the entity type Pokemon. And you get the same result, just a little bit different structure, which is typical for Sparkle. So that concludes the quick introduction. And now I'm passing to Andrew, who's going to show some examples and applications of this query functionality.
So I'm going to be talking a little bit about the entity query applications that you can do with some of this new stuff that Tony showed. And so I'll quickly show off some of the examples that we've prepared. We'll look at a few examples because there's a lot of them. We don't have a ton of time to go through too many things, so I'll try and just cover a few of the more interesting and perhaps more quickly understandable ones as well. So the first thing I'll look at is filtering continental plates by their geological period, where we'll use filtered entity class for that. And I also work on the food and nutrition content stuff, so I'll show a little bit about that with nutrient ratios, with you know, a couple of these things that Tony showed. And lastly, I'll quickly look at some award-winning restaurants and a neat data project that one of my coworkers was interested in, where we used an entity store to be able to use this stuff to do some neat things. So to dive right in, the first thing we'll do is use filtered entity class to write some Wolfram language code to be able to select geological periods who satisfy the condition that the time range is greater than the last 550 million years. With that, it's not too hard to go find those. which we can use with entity list, which if this should run in a second here, you can see that these are the geological periods that actually satisfy that criteria. So this is an easy way to use Wolfram language code to be able to query for this sort of information. We can also write another entity function here that grabs the continental plates from each entity, and then we grab the keys, which are dates, we sort them in order, and we make columns that have the common name, the date, and some geographics. So as a quick example, I'll show you what the result looks like for the Jurassic period, for example. So this is just the first and last frames that are produced for each one, but you can kind of see what they look like. So it says what period it is, and then the years on which they are shown. And with that, it's not too hard to be able to make a nice little animation here. Just by calling entity value on those periods with the entity class, and then using the plate outline entity function that I have there, then we just flatten the lists out and drop it into list animate, and then we get this nice little animation of the movement of the geological plates over the last 550 million years. So it's kind of a neat example there. Moving forward, we can go a little further, and I'll talk a little about food now. I saw some questions earlier about the control equals interface, or the natural language input. I've sort of done this here where I can just evaluate this real fast. And so basically, if you want to see how that's done, normally you would use control and the equals key to be able to pull up a new cell like this. And you can do, say, refried beans as an example, hit enter, and then it will come up with an entity you can look at here. And then if you click the little button, then you can actually evaluate that and have that stored there. So I think I also saw a question where someone was asking how these can be stored in variables. And just like this, you can just drop a symbol here, hit equals, and then it's stored in there. And if we do refried beans, now we get that. So this structure might look a little different than some of the other things Tony showed. This is an implicit entity, which means in the second argument, there is a list of rules that specifies how it is filtered down, and it represents sort of one food. And so this is using the food type property to narrow it down to beans and those that have been prepared as refried, and they don't have any extra foods added to them. So we can use extended entity class on this to be able to add a new property called the protein to fat ratio, where we take the protein content and the fat content, we divide them, and we'll use quiet to silence any messages that might happen. Like, for example, if the fat content is 0, it might, divide by 0, and that could be problematic. Moving forward, we can take that example there and use filtered entity class to only keep the number versions of that stuff. So any entities where the protein to fat ratio is a number. So we'll use number Q for that. Then we can also use sorted entity class to be able to find the 10 refried beans whose protein to fat ratio is greatest and put them in descending order, which we can do there. And then finally, we can pull that out with entity value, or this shorthand entity value syntax, to be able to see the results there, which I'll show here, where you can see, so on the high end, it's about 12 times as much protein, whereas on the end of this 10, it's more like 7. So that's kind of interesting to see that way. So that's a quick example that way there with some food things. I'll quickly go through this example next, which is involving award-winning restaurants. This is a more complicated example, so I won't be able to show it all, but it does touch a lot of our technology. For example, my coworker was really interested in gathering data on award-winning restaurants since he has a background in culinary science. And so he wanted to gather this data himself, analyze it, and then see if we could find some interesting things with it. So the first thing he needed was a data bin, which the Wolfram data drop allows you to add data to a continually collecting bin. And so you can use the create data bin function to build one, and you can use data bin add to add things to it. And then he used a web form in the Wolfram Cloud to be able to gather that information. He just built a simple web form to be able to enter the information on his own using form function and cloud deploy. And then he used an entity store from that data that he gathered where he used functions like dataset to be able to create the entity store. Lastly, from that entity store, he was able to register it and then do some interesting things there. There's actually a marketing page. If you get the notebook, there's a link to the actual page itself that goes into more detail on some of those other parts, but we're really only going to focus on the last part, which is about querying it. So the first thing we'll need is to download the entity store, which I have hosted in the cloud. And once we have that, we can register the entity store, which returns a list of the types that were added to entity values type system. And from there, if you take one of these, like the award-winning restaurant type, you can actually see the properties and those sorts of things that are available. And so he gathered a lot of information on cuisines, cookbooks, awards, and those sorts of things in order to kind of analyze and group them. Then from there, it's not too hard to write queries to be able to find restaurants that match certain criteria. So like, for example, this is an implicit entity class where we look at award-winning restaurants whose awards must contain 1 Michelin star. And then we can use sorted entity class to be able to sort them by opening date and then only grab the top 5, or the first 5 rather. And then we can use entity value to pull out the dates and their cuisines, which you can see here vary quite a bit, and the dates go back even as far as the 1800s even, which is interesting. Going a step further, we can actually look at a different subset by looking at, again, using the awards, so restaurants that have 1 Michelin star. And let's grab those whose closing date is currently operating, so that they're not actually closed, they're just currently operating. And then we can write another entity function here, we'll call it isInsideNYC, to determine if a location is within New York City. And so we can say, well, if it's a geo position, let's use geo-within-Q to be able to test if it's within the entity of New York City. So we can test this on one of our entities here, and we can see that this one is indeed inside New York City. With that information, we can take that and we can use filtered entity class to use that function we wrote to pull out the locations of the restaurants that match that criteria. And once we do that, we can plot it out, which I'll show here. So you can kind of see that it's not too hard to use GeoListPlot to be able to show that. And as one more piece of information to kind of take it a little bit further, we also used find shortest tour and travel directions to be able to find optimal real-world paths through all of the restaurants in New York City, either by driving or walking. I won't show the code here because it's a little involved, but I guess I'll show the result here, which is rather interesting, how the routes for driving and walking differ as an example in order to get through all of them. And with that, I think that kind of wraps up the entity query side of things. And so I think now I will jump over to my food presentation right over here. And so, as I mentioned earlier, I work on the food and nutrition content, and so I will be talking about this a little more here. So to give you a brief outline of what I'm talking about today, I'll give you a quick overview of food and nutrition in the Wolfram language, how it's organized, on that sort of thing. And I won't be able to show all of the examples that we have on our page, on the web page, but I will be able to go through a few of them. In particular, I'll be looking at price lookup codes, or PLU codes as they're sometimes called, and look at some brand name comparisons and labeling terms and how to compare those. And I'll also be talking about some ingredient substitutions and food groups, but more or less we have lots of information on packaged foods, nutrition, being able to look at dietary guidelines and that sort of thing, as well as aligning to cooking times and the Lingua L International Food Thesaurus. But unfortunately, I only have enough time to look at a couple of these things, so we'll move forward here. So to give you a brief idea of what is in how the food and nutrition information is structured in the Wolfram language, there are 3 approximate types that you really need to know. Food, of course, is the first one, which, as you might imagine, is the most common and most detailed actually as well. We have about 150,000 entities, and we have over 600 properties. And as you can see from the sample entities, these are very detailed. They have very long names, and they have lots of things to qualify what they need and that sort of stuff too. Additionally, food types is another type to consider, where we have quite a few less. There's only about 1,800 of them in comparison to the foods, but they're a lot less detailed. So for example, rather than a specific variety of apple, we only have just apple. Rather than chicken prepared a certain way, it's just chicken. And so this allows us to more fuzzily compare and sift through the foods that we have. One thing to point out is another type are what I'm going to call classification types for foods. And these can be found with the categorical property values property. And this shows the actual breakdown of how these foods are classified in our system. And so we have a system of about 10,000 entities and about 50 different categories to be able to write foods down, from how they're packaged, how they're processed, or what other foods have been added to them. So moving forward with some of that information, that's kind of the rough idea how the system is organized. Moving forward, let's look at the first example here, which is about PLU codes, or price lookup codes. These are codes that are used worldwide in like grocery stores to classify and label produce, among other things. And so we have now entities on those. So these are just simple 4-digit numbers, as you can see here, where there's a lot of information about them, including what category they belong to. Are they fruits, vegetables, so on, as well as what commodity, which is sort of like a food type in a sense, so bananas, asparagus, apples. And then there's also information on specific varieties that correspond to each PLU code. Additionally, there's also other information, including like sizes, whether it's large or small, and that sort of information as well. And the nice thing about these, if you've been to a grocery store and you've seen the fruit or other produce typically has barcodes that look kind of like this on them. And the nice thing is that the built-in function barcode recognize can actually read that without much trouble. And in fact, here I'm just doing a quick string take operation to pull out only the portion of the stuff that actually has the PLU code in the barcode. So you can see that number is pulled out from there. Now you'll have to, once you have the number itself, you can put that in as an entity. And here I'll just use dataset to be able to see a couple properties for that. And you can see that it does belong to lemons. It's for large lemons, and the size for a large lemon is defined to have a diameter of at least 65 millimeters. And we can also see that it's aligned to the lemon food type, as well as a few foods in our database, for example. And if you don't believe me, because that last image just had the numbers on it, barcode recognize is indeed using the barcode itself, not the numbers. And so you can see here that this one is for a 1-1, which is for a banana, for example. And we can produce more information out of it, like to be able to pull out that it is a banana using the food type property. And we can also produce nutrition labels from that information as well. So that kind of wraps it up for PLU codes. And I'll move forward to food brand names. So here we have one of the types that we have for classifying foods is brand names. So here I've just grabbed a bunch of different brand names that might be recognizable. And here I can use the foods property to be able to find the foods for them. So for example, if I look at a particular brand, I can see these are some example foods. And we can take a look at how many are in each one here. So it's a handful of foods for each one, as you can see. And another nice thing about our data is that we also have images for a lot of packaged food. So for example, here, this is just some example images that we have for these brands here, as you can see. There's a lot of planogram type images that we get for all of these things. So with those images, after we've aligned them for each brand, we can also find the ingredients for them. So for example, for this particular food, these are the particular packaged food ingredients that we actually have for it. And so we can take a look at all of those by aligning them to the brands. And we can see that if we look at how many are in each brand, it looks like French's has a lot more than, say, Coca-Cola, for example, it looks like. And from that information, we can use feature space plot to see kind of how they all relate in a 2D way. And so this uses machine learning and neural networks to be able to determine where they are. And here I've just used labeled to be able to show the image for them. And so you can kind of see that sodas are somewhat grouped together, pastas are kind of grouped together, and so are these two candy bars, for example. And mustards vary a little bit depending on what kind of mustard it is, it seems. But they're kind of in the middle, somewhat together as well, which is kind of a neat way to look at things. So moving forward, you can also look at them in a different way. One way I like to look at foods is in 3D nutrient space. And so here, if you see, this is fat along this axis, protein along this axis, and then carbohydrates along this axis, you can see where the different foods live in that area. So you can see candy bars are way out over here, the pastas are way over here, and most everything else is kind of low on this end because they're kind of low on protein. So moving forward, we can look at another way to look at foods is labeling terms. And so this gets into a little more, a few more of the categorization type properties that we have. And so we have entity types for fat labels and words like that. So these are kind of like marketing labels if you want to think of it that way. So here's just a couple I grouped together. We can find all the foods that are attached to each label. And I guess I can open this up and you can kind of see, for example, for non-fat, it looks like mostly in the opening few of these, it's a lot of non-fat yogurts, for example. Going a little further, I have some code here where we can use box whisker chart to be able to take that information and show it all together in a meaningful way. So in this case, I'm looking at just the fat label terms in terms of calorie content. And so you can kind of see how the higher fat terms are actually have more calories to them compared to the lower fat versions, which is kind of interesting and neat. And I have a similar thing for, sugar labeling terms, so you can see sweetened is further to the right on average than say no sugar added in similar terms that way. And another way to look at them is in 2D nutrient space with a little extra information. Here I'm using a bubble chart to be able to include the size as well, where the size of the bubbles are however many foods match them. So you can see the most common ones are terms like reduced fat and non-fat, for example. And you can kind of see that they spread around a lot in fat space and not quite so much in sugar space, it seems, with sweetened being the most, which is perhaps not surprising. Moving forward, some other information that we have includes ingredient substitutions. We have a lot of curated detailed information about ingredient substitutions. So for example, for allspice here, you can see this returns an association where the left-hand side, or the key, is an amount of a food, and the right-hand side is a list of entity groups which are possible substitutions. So for example, allspice can be replaced with ground cinnamon, ground cloves, and ground nutmeg, for example, in different proportions. Now, that might be a little difficult to see because it's a little messy with how much information is there. So one way to make it look a little better is to leverage some of the other information we have in the language, including images. So I have some code there where you can see where the left-hand side is shown now in a nice way, and the right-hand side is grouped together to see that what the actual foods look like with those amounts. So it's a nice, easy way to kind of see things there. So we have ingredient substitutions for explicit amounts. You may go, wow, 5 milliliters is kind of a strange unit to use. And the reason for that is that we use SI units as best as we can for those sorts of things. But we also do things in terms of ratios. So in this case, there is no amount in the left-hand side, and the amounts on the right-hand side of the replacement are all in terms of percents or counts, for example. And so this is by volume percents. So you can see that about 40% volume for these first two, and about 6% by volume. And the nice thing about this is that if you have a different amount of allspice, you can replace it with these just by multiplying using our quantity framework. And of course, if you want to go further yet, we can look further at more qualitative type substitutions. So you can see that substitutions can occur on, say, a food type level. So you can see that broccoli and apple have a few different kinds of food types that they may go to. And one might be able to think a little more about how to organize this or visualize this into a network. And so it's not too hard to do that. I will go to the next slide here where I've done this. And in the example, there's the code, and it's actually in the notebook as well, but I won't show it here. But this is a nice way to sort of group substitutions according to their groups, their food type groups, so like sauces, for example. And so the arrows sort of indicate are the relations between which substitutions occur. And so you can kind of see most of the time groups stick together for the most part, which is kind of interesting. And lastly, I'll move forward a little bit into talking about food groups for my last example here. And so one of the food group types we have is called a basic food group, which aligns to the USDA MyPlate, for example. So here I'm just going to import this image here, which if you're not familiar with USDA's MyPlate, they have this logo that kind of indicates the relative amounts of what you should have every day in terms of these basic food groups of fruits, grains, vegetables, protein, and dairy. And with that information, you can use our entities for that and align them to the colors that the USDA wants to use for this logo, for example. So I just looked up in their style guide what the actual colors are, and they define them in terms of HTML colors, which RGB color now supports as a shorthand to be able to get those out. And so you can see when they evaluate to the actual RGB colors in the language. And from here, I won't be able to go into too much detail on this, but this code here more or less grabs all of the food types for each basic food group and then counts up how many there are in each. And we'll use that later. Another thing that we can do is look at that image, and the original image, we can actually use the new in 12 color detect and colors near to be able to, for a given color, find where those colors are. And you can kind of see the results here, pick out the individual areas on that image, which is really nice. So these are kind of like masks, if you want to think of them that way. And the nice thing is that you can pass this to word cloud, which takes as a second argument a mask, so that it will say make the word cloud in this area or to exclude a certain area, for example. And what we're going to do is set the color function to be the color for the food group that we figured out earlier, and use the image size option to be the same size as the original image. So that way it'll kind of line up in terms of that stuff. And then you can multiply the images together so that they will all sit on top of each other without colliding, hopefully. And the result actually looks pretty similar to the original. And so this shows that shows what the most common food types are in each group, while still maintaining the same shape and spirit of the original logo. And so that's kind of a neat example to show there. And I think at this point, I think I will turn it over to Alan, who I think will be talking about historical and cultural entities.
I'm Alan Joyce. I'm the Director of Content Development for Wolfram Alpha. My team is focused largely on domains that are outside of math and science, geographic, historical, cultural data about the real world and its representation in the Wolfram language, in the Wolfram knowledge base. So with version 12, as over the past few versions, there have been steady incremental changes and expansions across a lot of the domains that are exposed as entity types in the language. New entities, new properties, data updates, improved connections between entities of different types that enable more interesting computations. One of the more significant developments is just that all of our several hundred entity types are now fully documented for the first time. So if you go into the documentation center for the Wolfram language, this is the first time where any of these entity types, you can see examples, you can get a better sense of the scope and the capabilities of a given entity type, and lots of examples for each type. So today I'm going to be focused on a few examples from domains under the kind of broad umbrella of culture and history. So we've got some examples here from covering historical events and sites, historical countries and military conflicts, both of which have had a significant amount of work and expansion in version 12. Some things from kind of culture and media. We've got information about lots of different media types. I've got some examples to go through just showing how to work with data about books, artworks, also about movies. Another thing very popular that we've done a lot of expansion on is coverage of notable people across history and across cultures and different occupations. So some information looking at how you can explore genealogical connections, looking at relative popularity of people, making use of some of the alignment we've done between canonical entities in the Wolfram language and sources like Wikipedia, and also looking at some other data related to people like given name popularity over time. And finally, just some more broad kind of language and culture topics, looking at data about mythological figures, which is kind of interesting, and also looking at how you can explore and visualize data about languages, alphabets, and writing scripts. So just jumping in here, one of the things that we've really made some effort to do is aligning entities between types. So for example, a given historical site entity is going to have properties where the values of those properties are other entities in the language. So you can build up graphs of relationships between entities of the same type, of different types. You can use these to do interesting lookups and filtering of entity classes. So you can do things here like take an entity class of historical sites where the subjects that are commemorated include FDR, and with that, generate a geo list plot, look at the labels. So this has found a handful of historical sites that are associated with FDR, plotted those on a map. Same thing with historical events. There are many thousands of significant historical events in the language. We can find things where one of the people involved is Anne Frank, and then use this nice timeline plot functionality to look at all those historical event entities on a timeline. Historical countries, this is something where we really have put a lot of work into getting not only the countries themselves represented, but also having polygons for those countries throughout their history. So showing the extent of different countries, empires, civilizations, and being able to pull those into different kinds of computations. So say the Roman Empire, you can grab a list of properties here, let's say the rough start and end dates, and a polygon. Now the default polygon for a historical country is kind of the largest polygon in the series that we have, the maximum extent of that country or civilization, not the union of all the area that it has ever covered, but a period of time where it was at its largest. But then you can specify using dated wrapped around that polygon property. You can pick a polygon for a specific point in time, and then it's just as simple as putting that inside of geographics, and you get a map for the Roman Empire in the year 0. Those polygons can also be used in other kinds of computations, just applying geo area to any arbitrary polygon. You can get a rough sense of the total size of that polygon. We can also map geo area over a list of all the polygons we have available for a country, looking at the ebb and flow and the size and splits and schisms in those countries, and being able to plot the changes in size and land area over time. We can also take a look at doing lookups here. So here, for example, we're looking at historical countries. We want to find the 10 largest countries in a given year, and then apply geo area to those polygons. And here we get a list of those countries, and then we can take all of those and we can generate a map that shows all of those countries and their extent in the world at that time. Military conflicts is another interesting and very messy domain, but this is something where we're engaged in a lot of ongoing curation, trying to expand coverage of events and also the kind of data that's available. So for military conflicts, there's a huge range of possible properties here. We have, for a given conflict of any size, you can look at sub-conflicts going down to campaigns and battles and different kinds of skirmishes. Looking at commanders on different sides or in the different factions involved in conflict, looking at forces, looking at casualties. Depending on the data that's available for the conflict, this can go down to specific kinds of troops and armaments and casualties and destruction of war material of different types. But again, digging in here, we can look at, say, the list of battles under a particular conflict. There's 37 here, distinct entities that are connected to the Second Punic War. When you're looking at data for a military conflict, what you get back here is a list where all the data for a given property is returned on a list corresponding to the list of primary combatants in that campaign or in that conflict. So this is the Roman Republic and Carthage, and then whenever you get values for that, you've got those values in the same sequence that those actors are listed here. I won't explain the code, but this will be available in the notebooks that are shared. But with this data, you can do some interesting things like looking at all of those conflicts in a given war and starting to accumulate casualties over time and getting a sense of how that overall campaign may have flowed, how each side was affected. We can look at casualties. We can look at troop sizes used in each battle over time. And then we can do things like, look at changes in corresponding this with military conflicts and the actual historical countries involved, looking at changes in territory over time and seeing where there's some key inflection point in the course of that war where one side gained much more territory and the other side suffered some serious losses. Moving on from history, again, we have lots of different entity types covering different types of media, books, music works, albums, music acts, movies, periodicals, lots of different kind of data available for each of them. Something I don't think Andrew had mentioned, but and I've seen some people asking how to get all the properties of an entity on the chat here. But one of the simplest things, given an entity, or maybe you've done this by typing in control equals and then typing the name of the entity, just asking for a data set of values will give you all of the properties that are available for that entity and all of its property values. Similarly, you could do something like association. And give me 1 second because I think I've just had a crash. While I'm loading that up again, I'll just note that this is a page in the reference for the Wolfram language. There is a page that has a list of all the available entity types, and these are grouped by different kinds of categories. 1 second. And this is a nice way to explore, as I said, some of the syntax for calling different aspects of those entities, seeing some specific examples associated with each of those entities. All right, let's return to this. I am just going to expand this and we will finish working through this notebook here just to get things moving. Again, books, one thing, looking at a data set of property values. We can do some things here like constructing an implicit entity class, taking an entity class of books that were published in some particular date interval, everything in the 19th century, for example. There are 341 books that we've got represented as entities. And then you can do something interesting here like take some of those books and generate a word cloud where the authors' names are weighted by the number of books in that class. We happen to have a lot of works by Jules Verne, which may have something to do with our scientific bent in the company, but there's a lot of information here, including for works that are in the public domain, often the full text of books, which opens up some other kinds of analysis you can do. Moving on and looking at other kinds of art, artworks, lots of different properties of artworks, everything from creators and dates of creation to physical measurements, weights, heights, widths, diagonal measurements, aspect ratios. So we can do some things, say, look up artworks by a particular artist, get a list of all those artworks. We could look at artworks completed in a particular year and find those that we have some images for. You can also start combining some of these things. So for example, constructing an entity class of artworks by a particular artist, Jeff Koons, and then let's take the 30 tallest artworks and get a list of those. And then you can do things like For some of them, we actually have geopositions. They're permanent installations and we know where they're located in the world. You can look at those on a map. For others, we have images, and you could do something like make an image collage where the size of the images are weighted by the relative height of those works. Again, movie data, I'm going to move a little quickly here since we got delayed by having a crash, but we've got information on movies. You can pull up specific properties of a specific movie. Again, you could do an entity class here where we're saying, give me the 10 top box office grosses in 1980, and you get a list of those movies. And again, you can do things like, just to get a quick sense of their relative box office, do an image collage where they're weighted by that property value. People, there are several 100,000 notable people represented as entities across all time periods and countries and occupations, as I mentioned. One of the things we've been making more of an effort to do is establish connections between people. So certainly family relations are important, parents, spouses, children represented as other types of entities. And when you have that, it's possible to do some interesting things like using the nest graph function, start walking down through all these relations and construct a graph of the children of a particular person going down several levels, and you get a nice little slice of the royal family tree here. As I mentioned, we've got connections between entities in the language and links to external sources like Wikipedia, Wikidata. So you can use the Wikipedia data function, which is very handy. And I believe in version 11, we added a property to get the daily page hits for a given page in Wikipedia. So using that as sort of a proxy for general popularity of an entity, look up Wikipedia data, get page hits for John Lennon, plot that over time. You see some cycles, which may be tied to people's birth, death. They tend to come up in the news, other events that show up. We can again look at music acts with particular members. We can use Wikipedia to find and plot the relative popularity of those bands, which this should surprise nobody, I think. Apologies to Wings fans out there. Or again, just with specific people, find all the members of a given music act, and then apply Wikipedia data across those people and look at their relative popularity in Wikipedia. Given name data, also interesting. There are 116,000 plus given names that we have detailed historical data on from the Social Security Administration. So you can look at things like the fraction of all births and other registrations in a given year that were accounted for by a particular name. John, you very, very, very popular, steadily declining over the years. Although if you look at the overall rank, you can see even though the fraction may have declined, John was 8+% of all registrations in the late 1800s, down to less than 1% in the 21st century. The rank is still relatively high. We've gone from 1 down to 25, 27 maybe for John. There are some other interesting things you can do when you combine these with other entity types. Let's say mark the release date of Breakfast at Tiffany's and look at whether there was a surge in popularity of the name Tiffany after that date. It's kind of an interesting point there. Game of Thrones has surprisingly started to make a showing in these data sets recently. For anybody who follows it, I guess maybe it shouldn't be surprising at this point. Arya has been among the most popular of the Stark children, at least. And then just looking at the most popular names in a given year. For the latest year, it's easy to pull out the given names that account for the top 10 largest fraction of male and female names and plot those. Finally, just a couple of quick things. Going far back here, we do have data on mythological figures and a lot of different mythological traditions. So again, for a given figure, this is what I was trying to show before. You can ask for a property association, and you get all of the properties available for that entity and all of the values for each of those properties. You get a nice view of all the data that's available in the language that you can work with. You can, again, look up mythological figures that are a particular type in a particular culture, say deities in Greek mythology, and get a list of those. Using the filtered entity class functionality that Tony and Andrew had mentioned before, create a function where you're looking for other mythological figures whose symbols intersect with the list of symbols associated with Zeus, and then taking a look at what cultures those are from and what those specific figures are from. Doing some grouping by patronages, looking at which entities, which particular aspects of life have the most deities associated with them, and doing some other interesting things like take all of the mythological figures associated with the underworld, graph them and their relationships to other things that they are the patrons of. And finally, languages, alphabets, writing scripts. This is a lot of really, really rich, detailed data here. You can do things like analyze the lexical similarity of languages, generate graphs where you can start burrowing down and looking at the connections between languages and how closely related they are. And then things like writing scripts and alphabets. These are important, but there's subtle differences here. For Latin, for example, is both a writing script and there is also a Latin alphabet. The properties that are available for each are different. The alphabet is focused on the actual characters. The writing script is more some of its ISO designations and classifications, different aspects like, is it left to right? Are there other kinds of things? Is white space required between words? And all this stuff is represented in a way that's computable, and you can look up related writing scripts in that way. And you can do things like find other writing scripts that share certain characteristics, let's say everything with a bottom baseline, left to right writing direction that uses white space between words. Get a list of all those writing scripts. Similarly, other alphabets that make use of the Latin script, and just start digging down and do some interesting things like look at word clouds of all the characters weighted by the number of different alphabets that they appear in all of the alphabets that use the Latin writing scripts. Okay, I am going to pass things over to Keiko and I apologize for the glitch there, but we will move on with the presentation.
Hi, thank you, Alan. My name is Keiko Hirayama. I'm a developer in Scientific Content Group, handling biology and medicine data. And in this presentation, I'm introducing sets of biology and medical-related data collections accessible in the Wolfram language. And our goal is to make all biology computable, and we have been actively expanding the Wolfram knowledge base in the area of life science. And our curated data collections cover quite diverse areas, ranging from human and animal anatomy to animals and plant species to disease and genes. And in this notebook, we are analyzing and visualizing data using the built-in Wolfram language functions and looking at some examples from each entity domain that showcase the key characteristics of biological systems. So starting out by looking at anatomy areas, the anatomical structure entity domain provides information about more than 90,000 human anatomical parts. Here are some sample inputs entities. Anatomical concepts like organs, muscles, bones, and body segments. Those are known entities in the Wolfram language. And for each anatomical structure, over 120 properties are available to access additional details. For example, get information about skeletal connections of a bone. Of course, you can use Control equal and enter free form natural language query for conversion to inline Wolfram language input and evaluate it. So you can get muscle attachment, adjacent joint articulating bones information here. And in addition to textual data, 3D graphics models are also available, and we have models for over 6,000 anatomical parts. And this is showing the hand And in addition to human anatomy, now we have the new set of animal anatomical structure data available in the latest version 12. And the most recent data sets include computable information about canine, dog, and also horse anatomical structures. And like anatomy data for humans, various image and graphics properties are available. For instance, you can get the typical morphology of a horse brain, or get the image of the dog's toe bones viewed from different perspectives. And additionally, you can make use of built-in graphics functions to explore the internal structures of animal body. In this example, we use anatomy plot 3D function to visualize the joint of a dog. As you can see, meta information is baked in the model, and you see the associated entities for each subpart of the structure. And you can also add some custom stylings to this visualization. And here we can specify the tissue colors. In this case, we use anatomy styling option and specify muscles to be colored blue. And here. And additional plot themes are also available to customize your visualization. So plot themes like X-ray vintage styles, these are available as well. And in the next example, we use the clip plane options and fed into the anatomy plot 3D function to selectively cut outer layer, skin and muscles, to expose the internal structure in the graphics, like this. And with all these accessible tools, you can also visually compare the anatomical parts of an animal with the homologous, which means evolutionarily preserved structures. And in this example, we are comparing the feet skeleton in X-ray style, where one of the largest bones, this calcaneus bones, are highlighted in the graphics. And next one, this one involves a bit more coding, but we can also color associated structures and explore the homologous skeletal structures across different organisms. And now coming back to human anatomy, anatomy data itself was also expanded since introduced in version 10. And now it includes more detailed brain anatomy information. So let's take a brief look at the computational neuroscience area. Our collection of 3D anatomy models not only includes brain's large cortical areas, but also includes individual gyro structures and even smaller nuclei. So first looking at this is the brain's large cortical area, prefrontal cortex, viewed from different perspectives. And each subpart of this prefrontal cortex can be colored using anatomy plot 3D function with plot theme scientific plot theme. And also additional properties are available to help you categorize brain's associated function or identify its hierarchical relationships. And not limited to individual brain subpart, you can also analyze the component of a nerve pathway. And here you get the components of a human visual pathway. And here the pathway components. And we can feed those into anatomy plot 3D again to visualize the pathway in the graphics, and you can also see the smaller nuclei as well. And not limited to the large parts of the brain, you can also explore the neuronal network of the brain. And here you find neuronal output of a particular brain region by accessing this neuronal output property in the anatomy data. And we can visualize the connections using the nest graph function here. And this is the network. And also built-in mathematical graph functionality help us analyze the network further. And this feedback loop is one example. It's the key framework in any biological network to fine-tune the system. And you can, for example, find a specific circuit that involves, for example, amygdala and prefrontal cortex, and highlight in the graph. And you can also identify the optimal flow from the amygdala to the output structure, which in this case is the spinal cord, and also highlight in the network graph. And after looking at the components of the brain, let's explore the functions. Variety of cognitive process taking place in the brain can be categorized and hierarchically mapped, and you can get basic information about higher order brain activities and or other physiological functions of the human body by accessing the properties of anatomical functional concept entities. And you can get the basic information like its definition and hierarchical concepts and standard experimental tasks to assess those cognition. And in addition to this, you have an access to statistical maps of brain activity, which is based on meta-analysis of fMRI studies. And here is a sliced image of the brain, horizontally sliced during the visual face recognition processing. And with a very simple line of codes, you can also create the collage or statistical brain activity maps like this. And moving on to topics on animals and plants, we have computable data on popular domestic animals. And for dog breeds, we have entities describe over 300 types of popular breeds. And you can compute basic information like height, weight, and country of origin, and typical temperaments for individual type of dog breeds. And you can do fun things like sorting all dog breeds by their height to compare all dog breeds. Or you can do create a word cloud based on dogs' temperaments. And most recently, we also introduced data on horse breeds. And for over 240 types of horse breeds, you can get information like types, uses, physical characteristics, information about a horse breed. And you can make use of implicitly defined entity class function to selectively find a group of horse breeds with specific property values of your interest. For example, find horse breeds by uses or find by their origin. And another cool thing that you can do is analyze and visualize the relationships of horse breeds based on their ancestry information and find how they are likely developed historically. And in addition to breed data, we also have data on species taxonomy. Our database contains taxonomic information for 1 million organisms, and you can easily fill the taxonomic sequence information, this information, to the graph function and visualize the hierarchical organizations of species taxa. And in this example, in the next example, we use the graph union function to combine the taxonomic graphs of two separate species and illustrate how they are likely separated in the taxonomic trees. And similarly, plant entity domain provides information about 170,000 plants. And in addition to taxonomic information, you can access their plant distribution information in North America and use geographics function to highlight it on the map. Also, implicitly defined entity class function is useful to selectively find plants that have specific characteristics, such as orange flowers with mature height less than 2 feet, and find those plants. And moving on to other life science domains, our disease dataset is recently updated to include additional information about medical conditions and patient statistics. And this domain is closely related to other biology and medical entities. So for instance, you can look up ICD-10 entities, which stands for International Classification of Disease Codes associated with medical condition, or find disease associated with certain anatomical structure entities. And you can also compute statistical information. In this example, we compute the trend of diabetes prevalence in the world, and you get a time series data, and that can be fed into the data list plot to see the trend. The other example here, we get the disease prevalence rate by countries and map them using the geo-region value plot to see it on the map. And lastly, Wolfram Knowledgebase provides gene sequence data for humans as well as other model organisms. And this gene example is created by another biology developer, John Cassell. And you can make use of sequence alignment function to compare homologous gene sequences. And in here we take EME1 gene as an example. You can find EME1 gene homologs for the selected organisms. In this case, we selected mouse, rat, chimpanzee, and humans, and retrieve the reference sequences. And then use the sequence, this is a sequence, and then use the sequence alignment function to compare. And just for the demonstration purpose, we just selected the beginning sequence of the genes. And this is the aligned part, and this is the misaligned part. This is the alignment between chimpanzee and human, and mouse and rat. And you can kind of confirm that gene sequences for human and chimpanzees are much more similar than those for rats and mice. So this concludes the topics on biology and medical entities, and we are constantly expanding our contents to help students learn biology. So more to come soon, and we would be interested to hear what additional topics or functionality could be useful. So thank you very much.
Thank you, Keiko. And yes, as we close today, a survey form will appear on in a window in your browser that will give you the opportunity for everyone to put in any suggestions, ideas, or kind of their wish list for data areas and domains that you'd like to see some expansion or support for in the Wolfram knowledge base. Thank you everyone for all these questions that are coming in, I know, and thanks to our crew here, our presenters and others who are behind the scenes furiously responding to all these questions as much as we can. Um, Alan, I wondered if I might ask you to mic up again and respond to some of the questions that we've seen. We've seen a few of them that are, repeated by a lot of people.
I see this one that I think you're talking about is it possible to edit an existing database to add new personalized fields? Is that the one you're talking about?
Yeah, we did have a couple
Related to that?
questions like that.
I think probably this is better handled by Tony or Andrew, because this is talking more about sort of generalized entity framework functionality. I guess extending built-in domains with data from individual users, like creating new data
Oh,
sets
okay,
or
sure. Yeah, we
adding
can
properties.
open that up to the panel, and if somebody wants to ask us to send them the share, we can certainly do that if you want to share something.
But I mean, I guess one of the things that somebody could do is take a given entity type and create their own entity store with the data from that entity type, and then add or modify their own properties. Does everybody have my screen? Yeah. Again, in the Wolfram Language Documentation Center, there is one big sprawling guide page that has a list of all of the entity types that are exposed in the language. And like I had mentioned before, this is a couple of brief references here, as people have noted. If you want to enter some natural language input and specify an entity, control equals will bring that up. You can construct your own entity expressions. Entity and then a given property in brackets will get a property of a specific entity. But this is the whole huge list of all the different entity types. So we've got things from geographic entities, astronomical, transportation and engineering, culture, food and nutrition. The list goes on and on and on. And as I had noted before, maybe we can take one of the food types. Any one of these pages will have a box that gives you kind of an overview of the syntax that you use to specify an entity, to get properties of those entities, get a list of properties, constructing, doing lookups, doing an implicit entity class where you're looking up all the, for example, foods that have a given value or specification for a given property. These pages will list some sample entities, so you can get a sense at a glance, what are the entities in this domain actually like. There will be property lists that show you all the canonical forms of the names of those properties and a more readable description of them. For food, this goes on almost forever. It's an impressive domain. Some additional details. These are some general things that apply to all entity types. I had seen someone ask, how do you find out what the provenance of the data is? And for specific entity properties, you can directly query in the language for a source, which will return an entity that represents the primary sources that were used for that property. And then again, there are just lots of examples for each of these entity types. And these are all, if you're using Mathematica, if you're working in the cloud, whatever kind of you're using to work in the Wolfram language, any of these inputs are just click to copy one of these inputs, paste it into your notebook, evaluate it, and you can just immediately start working with all these things. And these examples will generally range from fairly simple, trivial examples of just working with very basic things to some of the more complicated kinds of lookups and visualizations that we've covered here today.
Thanks, Alan. And we're just about at the end of time, but maybe one last reference for the data repository as far as how that relates to sharing and storing custom data sets.
Sure. 1 second. Yeah, I think I'm sure there are a few Switch screencasts that we've got somewhere in Wolfram U talking about kind of curating your own data and how to submit things to the Wolfram Data Repository. But for anybody who, people who are interested in working with creating their own entity stores or taking some of the data that's built into the language and extending that and creating your own collections of entity types and things, this is one place where you can find some additional data sets here to work with. These are all categorized, and again, these are things where you can go into a specific data set. These are things you can call directly in the language and just start working with some of these examples and explore the data. You also can, directly create your own, sorry, I'm trying to pull up a window here. You can create your own entity stores. So if you're working in Mathematica, you're working in the language, you can create a new notebook and repository item. This will bring up a notebook that lets you define your own data repository item. So you can fill in lots of metadata, you can put data into it, you can submit it to this data repository and it'll be reviewed and shared with other people, or that notebook will also show you how to just share it to your own private cloud account, and then you can share it with whoever you want. It doesn't go through a review process, but it'll create a nice shingle with examples that you can use in whatever kind of field of work you're in.
Thanks, Alan. Appreciate that. Kind of just a on-the-fly little summary there. And we're out of time, but again, I want to thank everyone for participating today. Our next session will be 2 weeks from today. We'll be covering mathematics and scientific visualization topics. Everyone who's in the webinar now will receive reminders by email about that event. We'll also be sending you a link to our archive page. It's the same link that you've had before. And just to clarify some confusion on that, when you go to that broadcast channel link, that URL that we send in the email, you simply click on the video. There'll be one set of an archive video from the first webinar 2 weeks ago. There will be a second archive video appearing soon for today's sessions. And if you click on those individual videos, you'll see a download link appear in the area of the video controls on the screen, and that's your download link to the presentation notebooks that are all zipped together. So, and we've put out some links to that here as well. So you will be getting all those by email. Also, a reminder that there are Twitch talks happening every Tuesday and Thursday throughout these summer months. So check out the Wolfram channel on Twitch TV to see more from directly from developers as they share new functionality in version 12. And please do give us your feedback on the survey as that shows up on your screen. We are going to shut the session down now. We look forward to seeing you next time, and have a great rest of your day.